In this video, I'm going to talk about creating a stack using arrays. More formally, we can say that we are implementing the stack ADT using an array as the data structure. So up here on the board, I have drawn the small array that I'm going to use. And over here on the left, I have written the stack ADT operations that we're going to talk about how to implement. Once you've seen how those are implemented, it'll be fairly clear how the others are implemented. Okay, so the first thing that I need is, aside from my array itself, I also need another variable, which is frequently called top. And that variable is going to store the index of the top of the stack. So initially, the stack has 0 items in it, and the top of the stack is at position 0. So let's suppose that we have our empty stack and we push on D. Well, then D is going to go here, and the new top becomes 1. And top is always going to tell us what the location is of the next element to be filled. In other words, where the next thing is going to go. So top is here, and the fact that it has a value of 1 in it means that we have one thing in our stack. So size is very simple. We just return top. Now let's suppose that we push another item on. This one will be an E. By the way, stacks can contain other things besides letters. They're just easy for me to draw on the board. So when I push the E on, then I need to update top from 1 to 2, showing that 2 is now the first available array location and that there are 2 things in the array. And so far, I've been actually writing the value of the variable top, but it's a little easier to follow if I just draw it as an arrow that is pointing at the first open location. And so I'm going to use that arrow and actually erase this right here. So let's suppose now that we've pushed on a D and pushed on an E that we were to push on an F. Well, then that F would go here in the first available space, and the value of top would become 3, reflecting that we have 3 elements in here. And so what we've seen then is that the implementation of push is very simple. Suppose that they give us a item to push, then array sub top gets that item, and top is incremented by 1. And so that is the push operation for an array-based stack, excluding if we have to extend the size of the stack because our array fills up, because stacks can contain an arbitrary amount of data, but arrays, of course, can only contain a fixed amount of data. The book talks more about how that extension is done. Okay, so then we've seen the push operation done several times. Let's do it once more now that we see our actual implementation written up here. So let's suppose we push on a G. So array sub top gets that item, which is G, and then top goes up by 1, so top goes up from 3 to 4. Now let's try popping off an item. Well, popping off an item is going to give us the top item, or is going to give us the first available item, the item at the top of the stack, and that is actually G, because this position is empty, because top actually points at the first empty position. So when we call pop for the first time, that is going to return G, so that gives a G back, and then it's also going to decrement top, so that top now points again at the first empty space, and correctly contains the number of items in the stack. So then pop simply returns the item at position top -1. So we can basically write it as top minus minus and then return array subtop. And then on the board, I've cleared out the item, but it's fine to leave it there as long as we know that it's supposed to be an empty place and it can be taken. So you don't actually have to set array sub top to nothing down here, and in fact it would be complicated to do so. Okay, so let's suppose that we pop off another item just to show again that this works. So that's going to decrement top from 3 to 2 so that it points here, and it's going to return that F as the result from pop, and I'm also going to erase it just so that visually we can see that it is no longer the thing at the top of the stack. So now the top of the stack is E, and it also contains D because E is the oldest remaining thing, D is the second oldest remaining thing. So that an array-based implementation of a stack is quite straightforward, as we can see by my rough pseudocode here.